Hello, in this video I'm going to show you how to write up results for a regression analysis. And I did several things here that are of interest. One is I took our dependent variable, in this case it's the case fatality, and this is based on the coronavirus data that I'm doing every single day. Today's the 26th of April 2020, and I log transformed the case fatality because of its distribution. Didn't look very good when in terms of the regression, especially with the effects of the predictor on the regression. I found heterogeneity of variance, which I was able to correct once I natural log transformed it. And our predictor variable is this index that I've created called the HB65. So that's the H stands for, and B stands for hospital beds. So hospital beds per 1,000 in a country. So this is national data from international data from multiple countries. So HB65 is that I take the hospital beds per 1,000 in a country and divide it by the percentage of the population 65 and above. Now this has become an important issue because we see that there's a greater case fatality in countries where there's a gap between hospital beds and proportion of population 65 and above. Okay, so that's what I'm doing here. Now you'll see that I log transform both HB65, so it's log HB65, this is a natural log transformation, and the dependent variable, which is case fatality, but before that I actually had HB65 not log transformed. So this is where we're going to start out. So what I did, this is of course related to an assignment in your class, and I was asked about how to write it up, but I have to go through the whole process here. So these are the different countries that I have. So just in terms of using the drop-down tabs to run a regression analysis, you're going to go under Analyze, Regression, and in this case I'm doing a linear regression. It's a multiple regression because there are multiple predictor variables here, not just a simple regression where there's one predictor variable. We'll start without the log transformation of our independent variable, predictor variable. So log case fatalities are a dependent variable, and now I'm going to do this in multiple blocks just because this is what the assignment was in your class. I like things done in blocks so you can see what the change in the R squares, the proportion of the variance in the dependent variable predicted by the independent or predictor variables. So in the first case we control for population density. Obviously you have to control for that. And I asked for certain plots. Actually, I looked for the Z residual plot versus the Z predicted. So this is how I can tell if there's homogeneity of variance. There's a normal probability plot, histogram. No, this is not the same histogram I'm asking you for, though. Actually, I'm going to remove that histogram. It's not the same histogram I'm asking you for when I ask you to take a look at your dependent variable in and of itself. Check it for normality. So I'm going to remove that for now. For under options, everything's good. We don't need any of this. I don't use those bogus step down methods. I got the plots. Statistics, I will take R-square change. I want descriptives. Do collinearity diagnosis. So we want to know if how strongly correlated are the predictor variables. Ideally, they would be uncorrelated completely. You can ask for confidence interval. I like confidence intervals. And look at some case-wise diagnostics for outliers. We'll consider an outlier value that is greater than 3 standard deviations from the mean. That means that the probability of a value occurring at that level or larger is like 90, it's about 0.03% or something like that. And hit OK. Oh, that's step 1, right? I need step 2. I forgot that. Step 2, I'm going to put in my HB65 index. Let's see, where is it? Ratio of hospitals per 1,000. Okay, that's it. I'm not using the log transformed one yet. I'll do that later. And these are the results I get. So I get these descriptive statistics. And so what I'm going to do is I need to report that. You always need to report descriptive statistics because if people are trying to replicate your findings, they need to know what you did. Now here I only included 44 countries, so if you've been following my videos for days, you'll understand how I got to these 44 countries. But there's clearly countries that are, the most affected by the COVID-19 disease. And also, I try to pick countries from every single continent. And I'm not interested right now in this correlation coefficients. This is your model summary, so it gives you the R square and then the change in R square that occurs once you include this from the first model to the second model. So this first model was just population density. You can see that that model is not significant. The F change, I mean, it's changed from nothing, and then the change from having just that variable in the model density to including the HB65, you get a larger R square change, is 0.425. The adjusted R square accounts for model complexity, and this is a better measure of how your model can generalize to other samples in the population, or to the population as a whole, if you'd like to say that. So you see, this is the F change statistic. So this one, you need this for your own purposes, but clearly the R square is important. R square change. In terms of the F table that you like to report, you look at this one here, and the F that we're interested in is in the F value for the entire model. This is the degrees of freedom in the numerator and the denominator. We know how to calculate this based on some basic statistics to get the mean square. Mean square, you get you divide the sum of squares for the model, the regression, divided by the degrees of freedom to get this, and the same for the residual. The F is the model, mean square model divided by mean square residual. So that's something there. And then this is the table that presents your coefficients. And what we report is this table here. We'd modified, and we look at a collinearity statistics. Tolerances that are lower than 0.10 are considered indicative of multicollinearity, and VIFs greater than 10 are considered indicative of serious multicollinearity. We don't really have any issues there at all. So yeah, we can take a look at let's see. So this is what our plot of our residuals look like. So this is 0 here. These are standardized residuals, and would we like there to be no obvious pattern here? I mean, if we compare it, and I'm not going to show you what the original non-log transformed value looks like, but basically this is much more heterogeneous than it was previously. So this is the best we can do at that. So I accept this as a good view. Now, I also said let's take a look at the dependent variable, which is log case fatality. I can go under Explore and ask for it. So I take my log case fatality variable here, and I just want to get a nice plot, a histogram, because I asked for a histogram of these, and hit OK, and I'll get this nice little histogram here. It's not perfectly normal because you can judge normality based on skewness. If you divide 1.007 by 0.357, you get more than 2, and so this is already a z score essentially. So you can actually use what we know about the z table to determine whether something is a violation of normality. You can take a look at it and you see that's kind of skewed to the left because of this value here, right? So it's not perfect. Nothing is perfect, as we say. So that's a histogram that you'd present if I were to ask you to present a histogram. This is a nice box whisker plot. There's one value here that we should be worried about. But when it comes to countries, I don't know if I want to exclude countries, which is, let's see, number 44, which is country 44. Sounds like a country music station. Let's listen to country 44. Let's see what country 44 is. It's Qatar. Well, I can understand why that would be, because there's some very wealthy countries that, and the reason I'm including countries like that is because there's maybe more hospital beds than in other countries, or less. I don't know. So actually, it says less hospital beds per 1,000. So that might be why it's skewed negatively. Huh? Interesting, right? So, but because these are countries, and I don't have that much data, I'm not necessarily going to eliminate them from the data. So you'd actually have to analyze that and look at whether or not this there's an effect of this entry on our fit statistics, our what we call the, our outcome variable. Does it affect the coefficients of our predictor variables and our outcome? We can do that too, but for purposes of our analysis right now, I just want to show you how to write this up. So let's go back to our data here, our outcome, and let's take a look at this. Okay, so I'm going to go back to my original outcome, which is the same, which I ran earlier. Let's see. Okay, here we are. There you go. Okay. This is our outcome data. So I'm going to go ahead and put this into, copy and paste what I need into my document for the purposes of this assignment. First thing, I can use the descriptive statistics to make a descriptive statistics table. You always have to have one. So what we want in our descriptive statistics table is all of our variables, our dependent variable, our predictor variables. I want the means and the standard deviations for all these variables. It's nothing more than that. In fact, I'd like it to 3 significant figures, so I can do this. I can make this table even nicer. But you got our means and our standard deviations here, and notice how I have this little superscript here. I never like to leave anybody uninformed about what I'm doing, so this is saying this is natural log transformation. So just so people know, here's a figure. So for log case fatality, okay, so, actually I put in the standardized regression figure. No wonder it looks so different. So I'm going to take that one out, because that's not what I wanted actually. So, but that's what it looked like. I wanted you to present the actual value of the histogram for just for our dependent variable in the first case. It's right here. So I'm going to copy that and paste that into my document. There you go. So that's that. Although the other result is important too, to show that our residuals are normal. Okay, so so table 2 includes actually the regression coefficients in it. You need both models. So model 1 only includes the constant and population density. So what do I mean by constant and population density? So and I ask you to write the regression equation associated with this. So I'm going to just insert the equation here. So what I'm looking for here would be an actual regression. Let's do a predicted model. So I can use this beautiful utility we have in Microsoft Word and find a hat. So I'm going to put a Y, and then here I'm going to insert with a subscript. Actually, let me go backwards there. I put a Y, and then I'm going to subscript this bad boy here. I'm going to put a little subscript in there. Y sub I. So what this means is that each individual will have a predicted value. That's why there's an I. The hat means a predicted value. And then we start by putting in the constant. So our constant here is, and this is going to be for model 2, because this is the model that we're really interested in. It's this value here. So we can copy that in here. Copy. As long as I'm inside this nice utility, it'll make things easy. Paste, all right? And that's so plus population density. And population density, by the way, is not significant if you look at its p-value, which I'll show you in a second after I do this. It's not significant. So this is our first, what we call beta. That's not necessarily, it's just a parameter estimate. usually we think of beta as being a standardized regression coefficient. This is the unstandardized regression coefficient, but it's 0.001 times our predictor, which is density. I'm just going to write density. And this density is unique to the individual, so I'm going to put a little I there too. It's density sub I. But you'll notice that this regression coefficient doesn't have a little I by it because it's not unique to the individual. It's kind of common to everybody. And then also then we'll have minus this value here, 3.3555 times the HB65. That's our predicted model. Since it's a predicted model, there is no error here. It's a prediction model. We're not actually looking at the actual value as our outcome. Then we'd add a residual. So yeah, this is like different size. Why is this different size? This is Cambria. I'm actually going to make this whole thing, just make it all Arial, kind of like Arial 11. That's what we use when we write grants, Arial 11. There you go, everything's constant. There you go, everything looks good. So this is the model that I'm asking for. So now I could plug in the population density from a country. Oh, this should have an I sub I too. I can plug in the HB65 for a country, and I could give their predicted case fatality in log terms. Okay? That's what this is. So this is the regression model, the actual regression model. Okay, so let me just read you how to write this up. It says, Figure 1 presents the histogram of our outcome variable case fatality natural log transform. Table 1 presents the descriptive statistics for all variables in the multiple regression model. Now, I don't think I need this here. In the multiple regression model, generally you discuss something. For instance, if you're not, so I don't have any male and female here, but I might want to present some unique different, like my sample was 65% female, but you don't need to say that much. You don't have, because again, you never want to repeat what's in the tables 100%. You want to repeat some of it, but not all of it. I said we conducted a multiple regression analysis in 2 steps. In the first step, model 1, table 2. Notice how I refer to everything, and that's one problem I have with some statisticians. They just tell you stuff without giving you information about what they're doing, and that's really troubling to students or people trying to read their material. It turns people off. We included population density, population per square kilometer. That's what that definition of density, to control for the effects of density on case fatality. In the second step, model 2, table 2, we added our key predictor variable HB65, ratio of hospital beds per 1,000 population to it's actually the percent, so it's a percent of the population greater than or equal to 65 years of age. The overall model is significant, F2, so this is your F value here. I'm going to make this look nicer. Yeah, I'm like a stickler for everything being perfect, so I'm going to make this more perfect. Yeah, equals 15.127. P-value is less than P01. Where did I get that? I got that from, if we go back to our results, we see that those results are up here somewhere. I don't know where they had them. It's probably up here. Yeah, it's up here. The F table, it's 15.127 for the second model. And accounted for 43% of the variance in case fatality. I don't know if I wrote the right value in there. Let me double check that. I might not have. Let me see. It accounted for, yeah, I'm using the R-square, 43% of the variance. Now, if you use the adjusted R-square, you just have to make sure you mention that you use that. An assessment for multicollinearity using variance inflation factor and tolerance suggested that multicollinearity is not an issue in our regression model. i.e. the predictor variables are not overly correlated with one another, because I assume that a lot of people don't know what this means. Given our outcome variable is log transform, we can interpret our results in terms of percentage change for unit change in our predictor variable. So that's one reason I like doing natural log transformations, because it actually facilitates interpretation. Each unit change in the HB65 index, I should say each unit increase in the HB65 index was associated with a 96.509% decrease in case fatality. So here I give you how that was all calculated. So we can go to this subscript right here to calculate percent change, use the following equation. So this is really cool, because basically you have like log odds now. But you can do this in terms of percentages. This is really cool, because we log transformed it. So it's exponentiating this value, whatever the b value is, and subtracting 1 from it, and then multiplying by 100 to get the percentage. This is the reason I'm doing this, is because the predictor variable is not log transformed. If the predictor variable is log transformed, we don't have to do that specific chain adjustment. We can just go ahead and directly interpret in terms of percentages. So it's more advantageous to have both values as percentages. Now that's important if you're dealing with data that have like very horrific units and you want to talk about percentage changes. So here, now this is not, I wouldn't include this in your write-up. So that's where you'd be done, right up there. So I'm going to just highlight this. But this is just for your edification. Given we are not sure of what the units are for HB65, I reran the analysis, also log transforming HB65, natural log transformation. Our new coefficients for the effect of HB65 natural log transform on case fatality natural log transform is minus 1.084. Thus, we'd write this up as follows: for 1 unit increase for a 1%. So now we don't deal with units, because I had no idea what the units were. So 1% increase in the HB65 index, there would be a 1.084 decrease in case fatality. So isn't that freaking cool? I love it. So now I don't have to deal with anything that's uninterpretable. So that's basically what you have to do to write up your results. Look, it's a lot of work, but you want to be the best, just like I want to be the best all the time. I never say I don't want to be the best. So let's just look at this assignment to make sure everything is under clear. So the histogram for perceived academic performance. So I showed you how to do a histogram. I mentioned that you can natural log transform things if you want to make it easier to interpret. That's up to you. I showed you how to test for multicollinearity, right? Tolerance, I explained what tolerance, how to interpret things, and I showed you that in the video. Provide me the overall test result, I showed you that, and I showed you how to make the interpretation. Write up a summary of results, including the R-square, I showed you how to do that. Include the actual regression equation, I showed you how to do that as well. So I showed you how to do everything. If you're thinking, well, how will I write up the table 1? Well, our first SPSS assignment, I gave you a table. You take that table and use it and adapt it to this. That's it. So yes, there's a lot of uncertainty here, but I'm going to act like Mr. Miyagi here for a second from the Karate Kid. Life is full of uncertainty, and the best statisticians, the best data analysts are the ones who can deal with uncertainty every day. So that's what I'll put as my final statement here. Like with the coronavirus issue, we're dealing with uncertainty every day. The ones who will survive this economic catastrophe are the companies, the universities, the people who can deal with uncertainty the best. All right, have a good day. Thank you for all being who you are.